Okay, so welcome everyone. Today we're going to be talking about mid-wave IR camera integration and specifically about Teledyne FLIR's product, the Neutrino family, of course. So just to do some introductions, my name is Ashley. I am the product manager for our Neutrino family, working here in Goleta, California at our OEM and components of Teledyne FLIR. And I started with FLIR about 4 years ago. And Ted.
So I'm Ted Conrad. I've also been here at FLIR about 4 years, and I'm the lead CRYOCOOLER design engineer.
Yeah, you started like a month before me, I think, now that I think about it. We both work here in Goleta. Mm-hmm. So Teledyne FLIR, what is Teledyne FLIR? I think many people are familiar with FLIR, and we've been around for a few decades now. But early last year, we were acquired by Teledyne. That hasn't been too much changes for what Teledyne FLIR is specifically. We're still the same FLIR, and now we are the largest division of Teledyne. And so we're the same FLIR with all of the resources of the larger Teledyne. So within FLIR, we make a variety of different products from detector, the infrared detector itself, which is shown here, all the way up to full solutions like security cameras. We make drones, a lot of commercial systems, inspection equipment, the FLIR One, which is the thermal camera for your cell phone. Specifically here in Goleta, we are the OEM and components group. So that is long wave, like the boson down here that you see, and the mid-wave solutions we'll be talking about today, which is the Neutrino. Here in Goleta, we are a merchant supplier, so we supply components into all of these other products for our other divisions, and we also sell externally to outside customers. So mid-wave IR has a lot of different uses, from the small swappy UAS solutions all the way up to fixed mount ground ISR solutions and everything in between. Obviously, there's a lot of military applications for this, dismount systems, intelligence, surveillance, reconnaissance, but then there's a lot of commercial as well. We have applications in firefighting, in gas detecting, surveillance, science cameras, security. So mid-wave IR can be used for a bunch of different things and can really help provide critical information for life-saving missions. So just to do a quick overview of what a mid-wave IR system is and what the subcomponents are, we've got this little exploded view here, and this is of the Neutrino camera. So starting with the very bottom is the detector, the focal plane array, which we do make in-house here. And you can have a bunch of different materials for that. You can have ISB, indium antimonide, you can have InGas, or you can have some of these newer materials, the hot materials that can go up to 120 Kelvin. And those are super lattice strain. So as these detector materials start to develop and new advancements come out, you're seeing a lot of different options available. Their pixel sizes are becoming smaller, formats are becoming larger, and so you're getting better resolution all the time. Outside of that, you package that in a dewar and a cold shield, and then you cool that all down with a CRYOCOOLER. And the CRYOCOOLER here is really what can determine the lifetime of your system, because it's a very complicated component and something that Ted's going to talk about in some detail in just a little bit. Outside of that, you wrap it in your packaging, which includes your electronics, and the electronics help control the lenses. They also provide any image processing algorithm you might need in order to get the best possible performance of your camera. In the front, we've got a faceplate for the Neutrino. Specifically, we have a standard faceplate that's available if you buy a Neutrino off the shelf. We also make custom faceplates so that you can interface with our camera in your larger system. And then the last component here is the zoom optic, and this is a really, really special and important part of an integrated solution. And that's because a really affordable mid-wave AR swap zoom lens has only recently started to become more available commercially. And that has enabled multiple fields of view in a very small package, which is something that wasn't possible just a few years ago. And because of that, you get something that's similar to what you would expect in the visible spectrum, but now you can have that in the midwave. And that's great because midwave IR can be especially useful over large distances. So we're here to talk about vertical integration today and how that can help your product. So what can vertical integration do for you? It really helps save time, gives you better performance, and it can also help save costs. So starting with the performance, the swap, when you have a vertically integrated product, you're putting together two subsystems that were designed to work together, and that gives you the best possible performance. It's not something that was kind of thrown together as an afterthought. So you can have something really tightly designed and optimized to work perfectly together. Budget, this one is pretty obvious, but when you have an off-the-shelf available component, then you're going to get the best price. We have 7 off-the-shelf configurations for integrated solutions, and that helps to reduce cost because there's something that might be available that is part of a larger production line. We produce thousands of these cameras every single year, and so we're leveraging improvements in supply chain. We've got the best people working on it, so we're able to bring those costs pretty low because we have such a large volume of manufacturing going through. It's not a unique custom thing that you're buying. You're buying something that leverages a larger manufacturing line. For risk, FLIR is a leading name in infrared because here in the Goleta facility, we have everything end to end. We have the engineers like Ted who do the design. We have the manufacturing in our world-class manufacturing facility. And then we also have a fully staffed product support team. So throughout the lifetime of the product, you know you're going to have people that are available to work on it. And you're going to get all of that from just one supplier. You're not going to have to go to multiple people or multiple groups of people every time you have an issue or every time you need some more support. Schedule, when something's available off the shelf, that means you can just buy it. And additionally, when you're using one supplier for multiple different systems, rather than to individual suppliers for each subsystem, you don't have to deal with stacking lead times. If you did this in the more traditional way of buying a lens from one company and buying a camera from the other, you might have a 4-month lead time from one and a 3-month from another, and then you might need another month to integrate the two together, align them, and test them. So then you're getting just a longer lead before you actually can get that product out the door to your customer or get it into the field. So schedule can be a really important one. And then for performance, these components are designed to work together, so you're getting the best performance. And performance doesn't just mean initial performance, it also means reliability over the product's lifetime. And like I said before, what can really impact reliability is these technically complex subsystems that have a lot of moving parts. Anytime there's a moving part, that's an opportunity for a failure. So 2 of the things that are the most complex here are the zoom optic and the cooler. And that's why the cooler is typically one of the things that helps determine what the overall lifetime of the product is going to be. So I'm going to throw it over to Ted, who can talk a little bit more about the coolers.
Okay, thank you. So I'm going to talk about the coolers that we use for small infrared cameras, and then also how we model and then verify the modeling of their lifetimes. And then finally, I'm going to introduce the FL100 cooler, which is the cooler that we use for the Neutrino series. So historically, coolers have been really either integral rotary designs or split linears for small infrared cameras. And the integral rotary coolers were probably far more common in legacy systems and continue to be very common. And they have some great advantages where because you have a mechanical linkage that connects the compressor and the expander or displacer, you're able to throttle the system easily over range of input powers. The STIRLING phase, which is an important parameter for the performance of the cooler, it does not vary with the RPM or the frequency that you operate the cooler at. And so you're able to achieve very compact system and a very fast cool down. But this is at the expense, because it's a somewhat unbalanced system, of generally high vibration. And also the linkages and the rotary actuator cause side forces on both the piston and displacer that tend to limit its lifetime. The systems are also known for acoustic noise, again, from the same things that are causing the unbalanced motion and vibration. And for some applications, that can be problematic, or it can require vibration isolation to prevent it from translating into optical jitter and interfering with the imaging of the system. Split linear coolers have been more common in newer systems, and it gets away from that high vibration and high side force by being kind of an inherently balanced design. So if you look at the linear motor that I've shown over here, you have dual opposed pistons, and their motions are largely balanced for the compressor. They're driven by linear actuators that don't generate very much side force. And so the side forces on the seals are reduced. And similarly, the displacer doesn't have anything that's generating a side force. The compressor and displacer for these are now pneumatically coupled, though. And so there becomes kind of a delicate tuning that has to be done so that they operate well together and with proper phase. And unlike the rotary cooler, you can't increase the frequency, to drive faster cool down. You're limited to really just increasing the stroke of the linear actuator and increasing the amount of power that you put into the system that way during cool down. But if they're well tuned, and if you get if you do carefully match the impedance of the expander to the characteristics of the compressor, you get very good performance, high efficiency, good cool down time. And with linear coolers, it's much easier to achieve long lifetimes, very long lifetimes. 20 to 30,000 hours is becoming kind of industry expectation for linear coolers. Whereas for the rotary coolers, the range has grown to 15,000 hours for certain designs and certain applications, maybe 30,000 hours. The linears, though, tend to have a longer lifetime. Go to the next one, I think, Ashley. You got that. So the way that we model and describe the lifetime of coolers, we use WEIBULL statistics and WEIBULL distribution, which is a distribution that is it models components that are subject to wear, mechanical components. If you look at the kind of classic bathtub curve figure here, this shows what the failure rate for a system subject to wear, like a cryocooler, looks like over a kind of as a function of time. And so you have it's divided into 3 regions. There's an infant mortality region, which is kind of exaggerated for the sake of the figure, but this is manufacturing defects should be a very small rate, should never leave the factory due to screening and burn-in processes that are done, that we do, that others do. That period is followed by a random failure region, where some number of failures in a large population will occur. In general, this failure rate is very, very low. And because of this, one of the metrics that is used for lifetime, the mean time between failures, which is the inverse of this failure rate, it can often be very high, even though it doesn't predict the true lifetime of the cooler. And finally, there's the wear out failure region, where the systems start to wear, and you see the failure rate come up until the entire population would have finally finished life at some point. This failure, or this region, is defined by the mean time before failure, which is the point at which 50% of the population of coolers would have ended lifetime. And the WEIBULL distribution models this. There are two parameters. There's a shape parameter, which kind of indicates the amount of wear present in the system, and the balance between the rim failure region and the wear out failure region. And then there's a lifetime parameter, which is the point. Well, it's the 63%, the time where 63% of the units would have failed. Often the lifetime parameter is reported instead of the actual mean time before failure, so the 63% point of the distribution rather than the 50% point of the distribution. And sometimes the mean time between failures is reported instead of the mean time before, which can be very misleading because of the low rate of random failures that occur during the life of a population of coolers. The mean time between failures can be much higher than the mean time before, even though it's not truly indicative of what the cooler's lifetime is. If you want to know more about the modeling, verification, cooler lifetime, and lifetime for the systems, we have a white paper, I almost forgot to mention, available on the website, and the link is down there below. And I think Ashley is going to email out later to everyone with the webinar a link to that as well.
Yeah, we will send out the links. Any links that we mention here, they'll be sent out following the presentation.
Okay, so this is kind of how you model the cooler statistics. But a question everybody would ask is then, well, where do you get the lifetime parameter, and where do you get the shape parameter of the distribution from? And so on the next slide, I'm going to talk about our life testing program that we perform here at Teledyne FLIR. So we do a combination of an industry standard SATA, or standard advanced Dewar assembly life test profile, and an accelerated life test profile. And so with different batches of coolers into each one. The SATA standard is an Army standard. It's been around for quite a while. It involves multiple cool downs at different plateaus of temperature and temperature ramps. It's a 72-hour cycle, which is repeated kind of again and again and again. Cool down time is measured, performance is measured, and the coolers continue to progress in that cycle until they no longer meet their initial performance requirements. That test can take a long time. When we talk about having a cooler with a 25 or 30,000 hour lifetime, we talk about 25 or 30,000 hours in the SATA test, which would be, 10,000 hours is approximately a year. So that you're talking about multiple years worth of test data to determine this. So when we want to get data more quickly, when we want to validate designs, keep an eye on current production batches, and the just kind of monitor our production as we go forward. We combine the SATA test with an accelerated life test, where we apply different accelerating stresses to different groups of coolers, and we then calculate what acceleration factor to the life test is made by those stresses. The ones that we use are ones that are commonly used by others as well. Additional load on the cold finger. So we drive the coolers harder by putting an additional heater load on the cold end, or we put them into a chamber and run them at high temperature. And both of those accelerate our life tests and allow us to get life test data faster than if we had to wait for every unit to complete the SATA test. And in all of these, we replenish the units as they fail with new production units, so there's constantly kind of a rolling replenishment. And we have a population large enough to start to estimate the parameters of our distribution. In the end, it's a relatively new product, and we're very interested to get the fielded experience from our customers. Thankfully, we have not had lifetime failures come back from customers yet, but as that database is generated by the actual customer experience, we will correlate that with the life test data that we have as well, and be able to to map our life test even better to real world conditions that people see.
Yeah, as Ted pointed out, it is a relatively new product. We've only had these in the field for, you know, a little over 4 years. Compared to many others, that's still pretty new, but we are happy that we haven't had too many returns for lifetime failures yet.
So yeah, with that, I'm just going to introduce the FL100 CRYOCOOLER, which is a miniaturized linear split Stirling. It's kind of the, to me, the heart of the Neutrino LC camera series. Other people might argue that the focal plane or the whatever else.
I think it's heart because LC stands for linear cooler. So it's more than the heart, it's in the name of the product.
So yeah. So it's a very small, very reliable and very efficient split Stirling cooler. We have, based on our life test results, what we believe is an industry leading mean time before failure of 27,000 hours or greater. We continue to do improvement activities on the cooler to try to increase this. We also believe that it is significantly more efficient than any linear cooler of the same size and class available elsewhere on the market. And that actually plays into the lifetime as well, because in all of the ways that you model lifetime, you talk about the number of watt hours that a cooler accumulates, how much power you put to it, how hard you run it, and the number of, as well as the number of hours. And a more efficient cooler, you're able to hold the same load, to run the same camera, and you're able to put less input power into it and stress the cooler less, and therefore it's able to last longer. And our design, the FL100, has a very, very high efficiency compared to other coolers of its size. And so the the lifetime that we have calculated and that we believe we have for this drives the lifetime of the product, and it has enabled us to offer a 2-year warranty on the Neutrino LC or the linear cooler based products that we have, so the NLC and the SX8. I think that's all I have.
Yeah, so Ted says it's miniaturized, just to give you an idea. It's really, really small. This is it right here. And it's enabled us to have a really, really great swap camera. So I'll talk a little bit about the camera itself now. As Ted said, it is completely enabled by this cooler. The cooler is what makes the product so tiny and so reliable. So we launched the Neutrino Swap series, like I said, a little over 4 years ago with the Neutrino LC. That is our VGA 15 micron format. And then we followed that up with our Neutrino SX8, which is our SXGA 8 micron format. And they're really great little cameras. The SX8 is a very little bit bigger, but essentially the same. And so you can almost use them as drop-in replacements for one another, because they have the same interfaces and all of that. So this is an SX8 here, but the NLC looks essentially the same. It has the cooler, and then it also has our hot FPA technology running at 120 Kelvin. It's another thing that is very critical to this design. And from those cores, we launched the Neutrino IS series, the Neutrino Integrated Solution series, which takes those cores and pairs them with zoom optics. The zoom optics are built in-house by our optical systems group. We purchased our optical systems group about 3-4 years ago, and they have enabled us to build these products completely in-house, which was something that we really saw a need for, and that we really think people would want to buy, and we have great success with those so far. It is very swappy as well. So this isn't an actual camera, but this is a model of what it would look like. And this one right here is the 25-250, which I'll talk about a little bit in the coming slides. But this is the size of everything, including the lens. So it's really great. It's really small, and it's very high performing. And we've got 7 different combinations available. And we can also do semi-custom developments, which I'll talk about in a little bit. So I'll show you some imagery. This is from our SX8 30 to 300 millimeter integrated solution. This was taken here in Santa Barbara at the airport. So here is a plane landing. You can see the wheels heating up over here. Zooming in a little bit here on that plane, so you can kind of see the performance over zoom. But I think in this one, it really shows the performance over the zoom. You've got a really, really stable image. You're able to keep things in focus throughout the entire zoom range. And that is incredibly helpful to our customers and really, really useful in applications. Like I said, mid-wave performs very well over distances. So having the option of multiple different fields of view is very useful for a variety of applications. So click to the next one. So here's our portfolio. This is the VGA option availability. So you can see here we've got a variety of kind of mix and match different parameters. We've got 2 different types of aperture on this product. We've got 2 different types of lens. We've got straight, we've got folded. You've got different weights here. Some of them are definitely a little bit heavier. And what you're trading there for weight typically is what your DRI is, your detection, recognition, and identification. So we've got a variety of different DRIs here, stemming from 12 all the way up to 16, 17, 18 even. It really enables us to have an off-the-shelf available option for almost any application that our customer might need. So these are all just the VGA format. We've also got the SXGA format, and same thing here, a few different options. You can kind of play with the parameters here and getting into some really good DRIs with that HD format. So why do you want to go with a vertically integrated, factory integrated product? There's just a lot of reduction in the development risk. Typically, you have to deal with your vendor for the lens, vendor for the core, and then maybe an integrator if you choose not to do that yourself in-house. So then it's just adding complexities and more additional failure points. When you go with a vertically integrated solution, you have improved time to market. The specification applies to the entire system. So you don't have to worry about the specification of the core versus the camera or versus the lens, and do any of those conflict. You've got one spec that covers the entire thing. And you also have one warranty that covers the entire thing. So the 2-year warranty that we get out of the linear cooler applies to everything, including the lens. So if you have an issue during those 2 years, you return it and we'll figure out what's wrong here. We'll figure out, is it the lens? Is it the camera? Is it something else? And we'll handle that for the entire thing. You don't have to worry about, finger pointing and who's responsible for what. It really enables much less complexity for you as the customer, and all that complexity is something that we handle before you even receive the product. So to dig into that a little bit more on what you have to deal with if you go with a traditional integration, it's a huge investment. And this is just an idea of some of the things that you would have to purchase in order to align, integrate, and test these lens systems. All of these things are pretty expensive, and they take up space in your warehouse. They take somebody who knows how to use them. This is a really, really niche technical skill. So you're paying quite a bit to get somebody who knows how to do this right. All of this adds up to a pretty penny. And if you use a vertically integrated product, then you've got your supplier who's making all that investment for you. And you're just able to get a fully tested and fully functional camera at the end. Saving time. This is something that I think is really critical. If you were doing anything traditionally for a program, something like a custom solution down here where you have your requirements, it could take you 28, 30 months to get into production because you're dealing with multiple different subsystems, you're dealing with different suppliers. There could be delays on one supplier's end or the other. You might get your lens and your core and you thought that you planned out the requirements correctly, and then you find that it's just not quite performing the way that you need it to once you get it in-house. And then you have to go back and figure out how to fix that. If you go with an off-the-shelf solution like the ones I just presented, then get that pretty quick. You figure out what you need, you qualify what we provide you, and then you're sourcing it and you're in production. There's this in-between niche here, semi-custom solutions. And that's really an interesting one. And it's something that we really enjoy doing here at FLIR. We had a customer come to us a little over 6 months ago, earlier this year, and they said, we really love all your products. We love these different lenses you offer and the different cores, but we like the 15 to 300 millimeter zoom. However, we don't want that with the SXGA format. We'd like that with the VGA format. And we said, okay, well, it's interesting. We don't offer that now, but we will offer that. So we did what we call a semi-custom solution, and we were able to put those two components together, qualify it and develop it here in-house, and then start shipping it. And it took us 6 months from when they told us that's what they needed to when they got their first product. And we're pretty proud of that. We think that definitely helped save them some time on getting what they needed in their hands and getting something into the field. Support and service. So this is something that maybe isn't in the foreground of everyone's mind when they start trying to figure out what kind of supplier they're going to use for their new product that they're launching, but it's something that becomes very important because every product fails at some point. It's going to fail. That there has to be some end of the useful life of a unit that's put into the field. And even before that, you're going to need support. You're going to need service. These are complicated systems going into an even more complicated high-level system. And so that is something that you will continue to need help with throughout the life of your product. And when that happens, if you used a traditional process here with separate vendors, you get a lot of finger pointing and back and forth. You get, you have some issue in the field, it comes back to you. You might try to diagnose which is it. Is it the lens? Is it the camera? Then maybe you say, okay, I think it's the lens. You return it to the lens supplier and they say, nope, this is the camera. Now you got to return it to the core supplier. And that's a lot of back and forth. It's a lot of spun cycles. It's a lot of sunk cost. And it's really just more time before you can get that back into the field. And that really can end up being a huge headache for you. And it's something that we try to avoid completely with vertical integration. So now if your system fails, you return it to us, we'll figure it out and get it back to you relatively quickly. So that is really one of the biggest values that you'll get over the lifetime of your product if you use a vertically integrated system. So the affordable total package is really what we're talking about here with vertically integrated systems. To sum up, you're getting something more quickly, you're getting something that performs better, that was designed to work together. So it's tightly integrated and it's really well optimized to work together. You're getting something to market faster, and you're getting better reliability. When we think about this FL100 cooler having a 2-year lifetime, you might imagine you've got something out on a security tower, and at times something fails, you go out there, you have to send somebody up to the tower, you have to pull the product from inside of the larger system, and then you have to bring it back. If you have a 2-year warranty, a 2-year lifetime or more, then that's just less than you have to worry about doing that, which is a huge hassle. So I think the reliability piece is a huge component. And when you do have an issue, you're only working with one group that will be able to help you with your problems. So we really think that vertical integration is a big winner for everyone. And we strongly suggest considering vertical integration for your products. So that really is, I think, everything that we had for you today for the content of this, but we can check out the Q&A section here. I see there was a couple of questions already, and maybe just talk a little bit more with the remaining time that we have. And yeah, if anyone else has any other questions, feel free to drop them in here, but we'll take a look now. Okay, cool. So somebody asked about mid-wave versus long-wave benefits of one over the other. It really depends on your application. Mid-wave, I mentioned, is great at seeing long distances. So if you're looking pretty far, that's something that you should definitely consider mid-wave for. Mid-wave cooled is much more sensitive than long-wave uncooled. There is the option for a long-wave cooled now. We have some long-wave cooled products ourselves. So you can get that option. But mid-wave can see things that you might be interested in, like gas leaks, methane. Mid-wave can see that, long-wave can't. Long-wave sees through smoke better, but mid-wave travels through the atmosphere a little bit better, is less affected by absorption, less impacted by high moisture atmospheres. So for any kind of application where that is important to you, mid-wave would be the better option. If you're trying to cut through smoke, then long-wave might be a better option. So it really depends on your application for that.
I would add to that a little bit too, on the cooler side. The mid-wave cameras operate at higher temperature, and we're able to use a smaller cooler. It's a smaller system for comparing a cooled mid-wave versus a cooled long-wave camera. That's obviously leaving the uncooled stuff out of it, but
Yeah, that's right. You get something really, really swappy with mid-wave because you can operate at the higher temperature. That's a really good point, Ted. Achieving the focal length that's larger than the overall length. So I would have to probably get back to you about the focal length question here, how lenses achieve a focal length which is longer than the overall length. I'm not an optical expert, but we do have a whole division of people who are. So I would have to get back to you on that question about the focal length. Let's see, what else do we have? Okay, interface options. The FLIR boson app isn't exactly what's needed for the Neutrino LC. There's a Neutrino SDK that goes with it, but it's very, very, very similar. It has all the same interfaces that you would normally deal with for the boson. So we try to make that completely common between all of our products here, that you have the same controls more or less. Some of the cameras have USB-C, some have Gig-E. For Neutrino LC and SX8, currently we don't have MIPI, but that's an option that could be available. That's something that we could potentially put in if somebody was interested in it. So there's a few different options available for what the interfaces are. I can just check real quick on the NLC. Let's see here. Okay, what else do we have? Folded optics explanations. So the folded optic, I'll kind of show here what I've got. So this is where the window is. Oh, sorry, I'll point here. This is where the window is that takes you into the detector. So the radiation is coming into here through the lens, bouncing off of some mirrors here, and then that is how it comes through here, something that's reflective in infrared. So it's using the physics of that interface here. You can kind of see how it would bounce and bounce into the detector. Let's see. I think pricing we'd have to talk about offline for different volumes, and it depends on the application for pricing. So that's something we would have to talk about separately from this here. Collimators, we don't sell collimators. We use them here, but if you purchase an integrated solution, you don't need a collimator because we would have already tested and aligned it using our collimators. So that's kind of an advantage of using vertical integration, is that you don't have to worry about dealing with collimators. Let's see. I mean, one thing I guess I wanted to mention, maybe a little bit more detail. I talked about detection, recognition, and identification. I just think that's a really interesting spec that we like to think about a lot, and it's something that can help you put into perspective what lens configuration you might want. So detection is the ability to distinguish that there is an object from the background. Recognition is what type of object is it? Is it an animal? Is it a vehicle? Is it a person? And identification is specifically what kind of person is it? Is a person wearing a hat? Is it a person with a bag? So each of those obviously has a different difficulty level, and that's why you're going to get your best distances for detection, your worst for identification. When we calculate DRI here, we use NVIPM, with the night vision integrated performance model defined by the US Army, and that's a pretty well accepted standard in the industry. And each of the tasks is assigned a difficulty level through that, where detection would be the easiest, and that's how we get into these numbers that we have. So yeah, and that kind of, I guess, goes to this question that just came in when I say midwave is better at long distance versus long wave. How far are we talking? For some of ours, we can get into 20 kilometers for detection. That's just for the ones that I had on the screen here. When you get into these really massive lenses, it can go much further than that. You can get into the 50 kilometers range. So we're talking about some pretty serious distances with these zoom integrated lenses. Fully integrated versions available now. Yeah, we have all of the integrated ones that I had listed on these other slides are available. So yeah, you can go to the Neutrino website here that's listed on this link, and it'll also be sent out to you afterward. And you'll be able to see all the things that are available. Okay. Ted, did you have anything else?
I think just one other thing to mention. I often get asked with the coolers, we have a lifetime in what we call the SATA standard environment and how it translates to people's applications. And the lifetimes of the cooler can be kind of application specific. There's a lot of things that come into how long a cooler will last in whatever it is out there doing. The number of cool down cycles. If you run something on top of a tower, it has a very different experience than if you put it on a helicopter and start it up every time you start the helicopter, for example. But the vibrations of helicopter vibration environment, the temperature that it runs in, we try to, with our accelerated lifetime modeling, we actually try to bring some of these factors in, and then we're continually expanding that accelerated lifetime test to try to bring more of them in, so we're better able to predict what our customers will be able to expect from their coolers, and to make sure that we have the longest life product we can possibly have for all the environments that they see. Yeah.
Okay. I think that's probably wraps it up. Jeff, is there anything else we should discuss before we adjourn here?
No, I believe there's one more question in the queue. No.
Oh yeah, so I didn't see that email yet, but I will respond to it. That is a specific email question, I guess, that I should have received. So I will go and check that email separately, offline.
No, but yeah, if there's no more questions from everyone, we'll be sending out a copy of the recording shortly afterwards. And as Ashley and Tad mentioned, we'll be also sharing the links to the materials that are noted in the presentation as well.
All right. Well, thank you everyone so much for your time. We really appreciate you joining us today. And yeah, if you my contact information here, if you have any other questions that I can help answer, or Ted, I can ask him questions too. I'm happy to bug him with anything that might come up. So thank you again for your time, everyone.